is talk to you a little bit more about how to detect objects in 3D surface data. Now, last time we talked about local representations of shape and how you might theoretically use those to detect the presence of objects in surface data along with other applications. But today I'd like to go into a little bit more of the practicalities of using those kinds of shape representations for detecting objects. So, just to remind you of where we are right now, we talked about various reasons why local shape representations are advantageous for a number of different applications of 3D surface data. They can help you with occlusion, clutter, partial views, redundant parts, and estimating the position and orientation of your objects in the scene. So, basically, the short synopsis is that global shape representations represent the shape of the entire object, as the name suggests, and that what you are going to sense when you sense a new scene in the world is not the entire object. You're going to sense part of the object because it occludes itself, for one thing, and you might also sense other stuff that surrounds it. And all of these things cause problems for global shape representations. And so, another level of overview is that there's sort of two different strategies for building local shape representations. One is to chop up the surface into non-overlapping sections, and each section gets its own shape representation. And the other one is to think of the world from a vertex-centric point of view. So every vertex on your surface has its own shape representation that gives a sense of what it thinks the world looks like from its position in the surface. So that's your overview that summarizes what we did last time. And now, armed with that kind of local shape representation, you might be asking yourself, how exactly would I write a computer program that takes a novel scene of the 3D world as sensed by one of my sensors, takes that in as input, and then uses those local shape representations to detect the presence of objects in them? And just for the sake of argument, I'll show an example of this. Excuse me, with one of those vertex-centric shape representations is what is being used for this. But the basic approach is like this. You're going to have some set of shape representations on your set of 3D models of interest. This is called a model library, the notion being that you have a database of 3D models, in this case of various kinds of toy things, but for more practical applications you can think of CAD models of furniture, CAD models of industrial parts, CAD models of various vehicles for a military application. And what you're going to do is for each one of your neighborhoods, either one of your vertices or each of your neighborhoods that are defined by breaking up the mesh into non-overlapping segments, you're going to compute one of these shape signatures, and it's represented by a little plate. I guess it's almost like a sheet of paper. That's going to be your local shape representation. So the robot man or the action figure is going to give you some set of these shape representations. Mr. Potato Head is going to give you another set of shape representations. And then what we're going to do is we're going to take a snapshot of the scene, and the scene is going to look like this. And the most naive thing we could possibly do is take all... and by the way, when we sense the scene, we're going to have a set of neighborhoods here, either, again, defined using a vertex-centric point of view or by breaking up this surface into a set of non-overlapping parts. And each one of those neighborhoods is going to give rise to its own set of shape signatures, a.k.a. feature vectors that summarize the shape in some way, a.k.a. a local shape representation. So the most naive thing we can do is take each and every last one of our shape signatures that we get from the scene and compare it to each and every last one of the shape signatures that we got from all the models in our model library. So it should be clear, just by the way I'm telling you about it, that this is probably not very good in practice. And it should be obvious why. So if you have 10 objects in your database, and let's say it takes you a minute to do this matching from points in the scene to points on models, then if you have 20 objects in your database, it's going to take you 2 minutes. It's going to take you twice as long because there are probably going to be about twice as many of these local shape representations. If your scene becomes twice as big, it's going to take you twice as long to represent something, or to detect that an object is there. So you should already be able to tell that there's something not too good here that we can improve upon. And just a little bit more formally, let's say that roughly speaking, let's say that we have m neighborhoods or n shape signatures on one of our models, and there's n in the scene. That means that there's going to be basically m times n number of comparisons we're going to have to do between local shape representations on one and local shape representations on another. So this has kind of an n squared kind of growth thing going on, where if there are n over here and n over there, it's like n squared number of comparisons. And by the way, and again, going back to the idea that we should be able to grow our library to have larger and larger numbers of models in it, well, basically, if there are k models, then you multiply that number of comparisons by k. So it's starting to smell like an n cubed kind of computational complexity, which is not so great. It grows polynomially. So, and there are a couple of key issues besides, well, let's see. There are basically two key issues that come into play. One of them is scaling up, which is that your computation time grows polynomially with the number of neighborhoods and the number of models. And also, the other issue is that the way I've put it to you is that every comparison of a local neighborhood on the model to a neighborhood on the scene is done independently of the other. And so, for example, I am going to hypothesize, or I'm going to test whether this location on the rubber ducky should correspond to this location in the scene. And then later on, as I keep moving forward, I'm going to, independently of the result of that, test whether this location on the ducky corresponds to this location on the scene. So hopefully it should be clear. Well, actually, it's not very clear. Well, I'll just tell you that this is actually a scan of the rubber ducky right here. So this is the hat part, and this is the body and the tail and such. And the reason why you can't see this part is that the 3D data was captured from sort of this point of view, so that this part was occluded. But at any rate, it should be clear, or at least you should be getting a hint that something's not quite right here, because it is simply impossible for this part of the object to correspond to here and this part of the object to correspond to here, since we are assuming that the only geometric transformations we have to model between the object and the scene is a translation and rotation. There's no way to translate and rotate the rubber ducky so that you get this part aligning to here and this part aligning to here. And unfortunately, it turns out that on this particular object model, there are locations on this part that kind of shape-wise look a little bit similar to parts on the hat. So you could, in fact, end up, after you do all of these comparisons, if you choose to do them, you could end up with correspondences between here and here, and correspondences between here and here. So you have to resolve them. In other words, you have to partition them into groups of correspondences that collectively make sense. Because if you just take all of them and try to calculate a transformation between the model and the scene that satisfies all of them, you won't be able to. So how to deal with these inconsistencies amongst correspondences? Well, here's a couple of recipe slides. There are several ways, and they're basically a bag of tricks that we employ to scale up this algorithm so that it has better runtime than this polynomial thing, a k times m times n. One thing that you can do is, excuse me, I have a cold. One thing you can do is reduce that k times m part, which is basically saying changing the way that you represent your database of objects, because right now we're thinking about our database of objects as being one long linked list of shape signatures, if you will. It's just a table that has one shape signature after the other after the other. And so you can imagine that if you and you're going to put together your database before you start looking at scenes, right? So you can imagine that you have this big set of data in a big table, and you have it, and you can imagine doing an offline kind of optimization, much like databases in other domains are optimized offline before you start doing queries on it. So that's the first thing you can do, is optimize your database for fast and efficient searching. So here are a couple ways to do that. One is to do what's called indexing, which basically means that you put your shape signatures for your models into some kind of a smart data structure that allows for fast querying. Something like a hash table or a geometric data structure that allows for fast proximity queries. Which is to say, fast ways to determine, given a new shape signature, whether it is similar to a set of pre-existing ones without comparing to each and every last one. And there's ways to do that, and again, following our image processing theme, there are a set of methods for doing this that were developed for data mining and statistics and other fields, and that have been basically hijacked for application to image processing. The second thing you can do is go back to this notion that I talked about last time, that local parts of distinct objects sometimes look similar to each other. And so in fact, there are some objects that belong in categories together, categories like minivan or tank or pickup truck, where entire regions of multiple objects look, in fact, identical to each other. An extreme case of this would be something like if you had multiple object models for different models of, say, for example, Ford trucks. But in fact, on the assembly line, the fenders for all of the different models of Ford truck are identical to each other, and that the thing that differs from one to the other is that one has a king cab, the other one has a bigger engine, the bed is different, whatever it might be. So in fact, in that case, it's not just that the shape of a part of one model is similar to the shape of that same part of another model, but they really are, honest to goodness, identical to each other. In less extreme cases, you can imagine having many different models of minivan from different companies, but really the back end of them all very much look similar to each other. So that's called shared signatures. And the notion then is that instead of comparing every shape signature of every Ford truck fender model to what you see in the scene, you'd basically have one collective shape signature that covers all of the different Ford truck fenders. And that basically reduces the number of comparisons that you have to make between your model signatures and your scene signatures. The third thing is what's called constrained correspondence search. And this basically goes back to the reasoning here having to do with the fact that you can't have both this correspondence and that one in this scene, because there's no way to rotate and translate this model to get it to end up like that, respecting both of those correspondences at the same time. So simply put, what you can do, if you first find that this part of the object corresponds to this part of the scene, you can simply skip this guy and not even check it, because you know that it's impossible. And you can do this if you are fairly confident that this correspondence is a real one. But that's the catch, though, is that if you start excluding the possibility of some correspondences later on, because some of the earlier ones are pretty good, the earlier ones had better be right, or else you have just caused problems later on in the process. So it's constrained correspondence search. Kind of a different version of this idea is what's called transformation clipping. In some domains, you might know beforehand what the range of reasonable geometric transformations between the object and the scene are. Here's an example. Let's say that you are traversing a part of Mars in your Mars Pathfinder robot. You know that there are no pre-existing terrain maps from Landsat because there's no Landsat on Mars. So what your job is to incrementally, step by step and meter by meter, build up a terrain map of this location of Mars that surrounds you by standing still, getting a scan of the environment from your stereo camera rig that's attached to you, then walking a meter, taking another scan, and then aligning locations or local neighborhoods on the first scan to local neighborhoods on the second one. So why might you know something ahead of time about what the possible range of transformations are? And basically what this amounts to is getting an estimate of how far you moved, basically. Because if you took a scan and then moved a meter and took another scan, then the geometric transformation that aligns them is going to be a 1 meter translation. And maybe you rotate it a little bit, so there will be a little bit of a rotation and a translation. But still, you have some notion about what the range of plausible geometric transformations could be. So for example, you know that the second scan, in order to align it properly to the first scan, should not be completely flipped upside down. Because that would imply that your robot flipped upside down in between scans, which you know didn't happen. Similarly, you didn't fall over on your side, probably, so there shouldn't be a 90-degree rotation either. And also, most importantly, in the up and down direction, the Z direction, if you will, there's probably not much of a translation in that direction either, because it would suggest that your robot started to fly in between scans. So this is called transformation clipping. It's called clipping because you are basically, you can visualize it as there being a 6-dimensional space of possible rotations and translations from your first scan to your second one. Translation along the X, Y, and Z axes, and then rotations about each one of those axes. So there's a 6-dimensional space, and you're kind of clipping off entire sections of it to carve it down to just those that are a priori plausible based on what you know about your sensor rig. That make sense? The other thing you can do if you want to take the other approach of reducing the number of scene signatures that you compare to is to do what's called queuing. So you can think of this as a quick pre-filtering of a large scene to reduce it down to just those scene signatures that you think could plausibly correspond to your objects in your database of interest. Now, this is not going to be a very, very precise test. And in fact, what's going to happen is that when you do queuing, you're basically going to stop the most implausible scene signatures at the door. And everything that looks like it might possibly maybe correspond to a part of your object in your model library is going to get passed through to do the full kind of computation-intensive comparison. But it's still going to have this property that completely uninteresting parts of the scene that look nothing like your object of interest are going to be stopped so that you don't do the comparison with them. And one example of a domain where this might be helpful is, again, if you have a 3D sensor in an airplane that is downward pointing and you are trying to detect objects in a vast flat domain like the desert. So if you take a scan of the desert, you know, your tank or your whatever that you're building that you are trying to detect might be a teeny tiny percentage of it, but the rest of the terrain being perfectly flat has very, very boring shape properties. It's going to have no curvature for one thing, and there's going to be no variation in that curvature as you look in a neighborhood around it. So you can potentially just say, I'm not going to look at any scene signatures that have low curvature. So queuing is this kind of idea. And this term kind of comes from psychology, where if we're going to look at something new, and we have some notion of what we're going to be looking at when we open our eyes. We tend to have our eyes gravitate towards certain parts of the scene as opposed to another because we are cued, we have received a cue for what we should look for. So here the idea is that you have your database has given you cues about what you should look for, and that allows you to quickly remove large parts of the scene. Does that make sense? Okay, good. Here's an example of an approach for indexing the database. In other words, doing this database optimization thing to try to speed up the speed of your queries. What I told you last time is that there are these things called spin images, which are essentially two-dimensional histograms centered around, each one is centered around a vertex on the surface, and it tells you about the distribution of points away from that point and up and down from that point in terms of its elevation. But since they are two-dimensional histograms, you can look at them as though they are images. And in particular, just as to remind you, if you take the spin images of points that are along this trajectory on the ducky, what you'll see is this set of spin images come out of it. One thing you should see right away is that they change relatively slowly and gradually as you go from one location to another. These two guys look extremely similar, and in fact, as you go from here to right there, there's not that much change at all in them. So that should give you a clue that these things are compressible. And luckily, you all did homework assignment 1, and so you know what PCA is and how to apply it to images. So simply stated, we can apply PCA to spin images to reduce them down to a lower dimensionality. So then, we start with spin images. We do principal components analysis on the entire set of spin images. And if you recall, one of your things you were supposed to do was look at the eigenfaces of your eigenface algorithm. This is the eigenspin images, if you will, for the rubber ducky. And one thing you can note right away is that the first several of them are kind of quantifying this kind of a shape, which must be prominent. And in fact, it should be prominent because the thing has a symmetry. So for every spin image you see over here on this side of the ducky, there's actually two of them because there's one on the right side that is identical to it. And so if you do what you were worried about for homework assignment 1, which is determine how many of those eigenspin images you need to keep around, you can in fact reduce the dimensionality of your spin images by quite a lot, especially if you only have to keep around a few of those eigenspin image coefficients. So then what's going to be the result of this is that you're reducing your two-dimensional spin image to a one-dimensional vector of numbers where that vector is small and only captures the first several principal components of the spin images. Then what you can do with that, after you do this compression thing, is basically represent, like I said, each spin image in terms of a short vector of numbers. And then think about that as being a s-dimensional vector space. And all of the points on your library of object models are going to populate this s-dimensional vector space. So then, if you're given a new point in the scene and you calculate its spin image, you can then project that onto your eigenspin image space to get a new short vector of numbers that represents that point in the scene. And then you can ask the question, for this vector of numbers, is there another vector of numbers that is proximal to it in this s-dimensional vector space? So again, we go back to this idea of proximity queries, where given a vector of numbers in some high-dimensional space, I want to get either the k vectors that are already in that vector space that are the closest to it, or a similar but kind of different question is, are there any vectors within a ball of radius epsilon from this vector from my scene? And then it should be clear that if you find other eigenspin image vectors that are close to the one that you're querying on, you can use that to get a sense of who this point in the scene might correspond to in terms of models. Excuse me. Now, let's see. So, in the worst case, if you're naive about it, if you have a total of n points in your object database, which is to say, I'm using m, n, and k a little bit differently. Sorry about that. I should change this. But here, if the total number of points across all objects in your object library is n, then the worst case, you're going to have to compare your new scene point to all n of them, which is a lot. But because this problem of proximity queries has been prominent in a number of different application domains, it turns out that nowadays you can actually get this number down to something like big O of log d, where d is the length of your vectors. So this is fantastic because notice that it doesn't depend anymore on the number of points on your object models. So if n keeps growing and growing and growing, you have a more or less constant search time for doing these proximity queries. And right, so that's the main thing, that this kind of puts a cap on or it slows down the growth in search times as you include more and more models in your database. And again, this is based on recent advances over the past probably 10 years or so in these geometric data structures for doing proximity queries. So, but as it applies to our problem of finding matches between a scene and a set of models, there are some key issues, which is, first of all, how large should k be if you're looking for k nearest neighbors? So here, I'm going to say that if I have a new point from the scene, I'm going to ask for the k closest vectors from the object models as potential corresponding points to it. Now, if k is too small, then you might miss the actual correct correspondences, but the actual correct corresponding point between yourself and the scene, or in the models. But if k is too large, then practically speaking, while the time complexity of doing this proximity query does not seem to go up with k, realistically speaking, it does. And then the other question is, how should you quantify the distance between a pair of vectors? So I've described it as a simple Euclidean vector space, where you simply take the difference between a model signature and your scene signature, and then take the L2 norm of it. But it's not entirely clear that that is the right distance for quantifying what is truly different about the shape of the two different regions in question. So this goes back to our familiar problem of trying to take our semantic notions of what our algorithms are supposed to do and stuffing them into mathematics. So it might be that if you have a set of object models in your library and a scene, and you simply explore what parts of your scene seem to be similar to what parts of your object models, you might find that there are parts that are totally dissimilar to each other that appear similar because you're using the L2 norm. And so you might say, well, wait a minute, no, this is not what I want. And so you might want to change the distance function, which is to say, change how you evaluate distances between scene signatures and model ones. So this is the question of what should D be? What should the distance metric between your scene signatures and your model signatures be? And I don't have any pat answers for what it should be, but it could depend on your application domain of interest. In other words, your own semantic notions of what it should mean for two signatures to be similar to each other. So that's the key issues there. Oh, right, announcements. Sorry about this. I left your midterms at my house. So I won't be able to bring them to office hours today, so you can't look at them. But if you want to see them, please email me, and I will bend over backwards to make an appointment for you to look at them at your own leisure. Alternatively, I'm going to give them to Jing so that she can show them to you during her office hours, which are on Wednesday. So again, the deal is you get to look at your midterm and the answer key side by side and ask any questions that you may have. But I put an announcement on SmartSide about this, but I hope no one shows up to office hours because they want to look at their midterm because, like I said, I forgot them. Please start, if you haven't already, start working on homework 2. And yeah, basically, just to repeat the usual refrain, the largest number of points that are lost on these homework assignments are because people last-minuted them. So start working early and ask us questions as needed. Any questions about administrative type things? Yeah? Okay, go ahead.
So are we going to get the tests returned back to us?
I'm going to keep them, actually, but you get to look at them in my office for as long as you want, as many times as you want, actually. But I'm going to keep them. Yeah?
Can we see the histogram of results?
I had that on Friday. I think I had the histogram.
The mean and standard deviation.
The mean is 54, and the standard deviation was something like 18 or 16. So again, just to repeat, if you are within a standard deviation of the mean, don't worry. And ignore what gradebook says about what your so-called letter grade is, because that's a bunch of hooey. In fact, it probably says that you all have Fs, because the mean score was F. So it has no rhyme or reason. Just forget it. Any other questions? Okay. So again, we started to talk about this last time, the question of shared signatures. So what we can do if we have a set of object categories, by which I mean something like SUV being a category, minivan being a category, pickup truck being a category, we can break up each one of those objects into parts using some algorithm that we might have for breaking it up into parts. Now, what we do after that is really up to us. The way I described it in the opening was that you would basically have one set of shape signatures for all of the SUV front ends, and assuming that all SUV front ends are similar to each other, and a set of, bless you, shape signatures for all SUV back ends, and that these would be distinct from the set of all shape signatures for minivan front ends and minivan back ends. But there's no reason to restrict yourself from that. So let's say that it so turns out that the middles of SUVs look similar to the middles of minivans. Then that's great. That means we get to compress the number of shape signatures that we store and keep and think about even further. We can just have a set of middles that include both minivans and SUVs in them. And in fact, if you just look at it from this point of view, I know it's very small and limited, but yeah, if you just isolate this part of this object and compare it to this part of this object, they look quite similar, even though they're from different categories. So what you can end up with is a kind of minimal set of so-called part classes, such as middles and back ends. And then if it turns out that SUV front ends don't look like minivan front ends, well, then that's fine. Then you can break those up into two different categories. And the notion, again, is that you're going to have one set of shape signatures for these guys, one set of shape signatures for these guys, one for these, and one for these. So we've just taken, if we have, I don't know, 40 different SUVs and 30 different minivans that are all slightly different from each other, we've then reduced them or condensed them down into 4 sets of shape signatures. And then what we're going to do at runtime is compare each scene signature to each one of these, each one of the ones in each one of the classes. So it should be something like, if there are, let's say, k different shape signatures per part class, then we're going to do k times number of part classes comparisons for each scene signature. It's But that, you're not especially out of the woods if you do that. By that I mean you basically end up with a set of correspondences between points on the scene and one of these part classes. So then you have just added a new job for yourself in return for making the time complexity of this scene to model comparison much faster. In fact, what you end up with is a second problem of resolving these correspondences between scene points and model part classes. And so then what you would do is try to refine that further by saying, well, okay, if there's a big cluster of middles correspondences in one location in the scene, then I'll assume that that's a middle of something, and then compare each minivan middle shape signature to those guys. If there's a large set of middles correspondences to one location in the scene, and there's one front end correspondence in the middle, maybe you can weed that one out, and so on. You can imagine how the next stage of trying to find objects in the scene becomes a lot simpler when you reduce the problem to when you first reduce the data that you start with to a set of correspondences with part classes. So the way queuing works is basically that we start with our set of object models in our library, and we calculate the set of our set of signatures from those models. And again, each model signature, each spin image or shape histogram or whatever you want is represented by something that looks like a sheet of paper. So let's say we have a big pile of those from our rubber ducky and from our Mr. Potato Head and from all of our other objects in our object library. And furthermore, well, no, let's just stop there. So, and let's say that I use techniques from machine learning to build a classifier. So a classifier system, what it does is it takes examples of one category of object and examples of another category of object, and then builds a computational mechanism that, given a new object, puts it in one category or the other. So what this classifier can do is use shape signatures from our model objects and shape signatures for either from, well, in one, like the easiest thing to think about is that you have scenes in which your object does not appear. So those are kind of the negative examples. None of those guys correspond to objects in your library. And all of the signatures from objects in your library correspond to objects in your library. So you can build a classifier that tries to discriminate object signatures from scene signatures that do not correspond to your object. And the key thing is that this better be a pretty fast classifier to evaluate in practice. Because what you want to do is take a scene that is huge and has, say, 1 million points in it, and very quickly say, yes, no, yes, no, yes, yes, no, no, no. And so one key characteristic of this classifier is that it has to be tilted in some way. And by tilted, what I mean is that some errors that it makes are more costly than others. So let's think about this. Usually, when you train a classifier to discriminate between objects in one category, let's say objects in category A from objects in category B, mislabeling a B as an A is just as bad as misclassifying an A as a B. But here we don't have that. And in particular, if you misclassify a point on the background as corresponding to one of your objects of interest, then maybe that's not so bad. Because what's going to happen after you do this classification is that you're going to do something longer, more time-consuming, more rigorous to determine if that point actually corresponds to something on your object. But if you make the other kind of mistake of saying that points that are really on my object of interest actually are not and get thrown out, then you're in bigger trouble. Because you can't vet that decision by doing any kind of later process. You basically throw it out. So in the worst case, what you could end up doing in this quick pre-screening of points in your scene is actually remove all of the rubber ducky points. And then you're left with nothing. You cannot possibly find a match between the ducky part of the scene and the ducky in the database. So when I say that the classifier has to be tilted, it has to worry more about calling ducky points non-ducky than calling non-ducky points ducky. Or the more technical way to describe this using the machine learning lingo is that it has asymmetric misclassification costs. And so you have to worry about that when you build these things. Is that clear? And so, yeah, this just gives a few more numbers to try to put numbers on what I just said. That basically, even if you misclassify a fair number of non-model points as being model points, but you still remove a fair percentage of the background from the scene, you're actually doing quite well. So here's an example where I did this in my first year as a grad student. I had an object model of a deer that's shown over here, and I took a large panoramic 3D scan of a scene that included the deer in it. And the particular classifier I used basically took each bin in my spin image independently and looked at the range of plausible values for that bin in the spin image and tried to decide whether each bin individually looked like it might be part of the object model or not. And so in a sense, each bin in the spin image provides a vote where yellow or red votes makes you think that you're strongly, highly likely of being on the deer. Blue votes mean that you think you're really unlikely to be on the deer. And so when you coalesce these votes over all of the bins in the spin image, what you can do is basically add them up and threshold them such that points that give you a lot of votes are passed through this queuing process, and then the next step is to more rigorously try to identify matches between points on the object model and points on the scene. The 3D-ness of the 3D data set almost completely goes away, but this is the deer and this is a table. And these are the votes that the signature on the deer gets, and this is the votes that the point on the table gets. That make sense? Some results. So basically, points that pass through this queuing process get shown in red. The U-shaped plumbing part is in the database, and the stairs are not. The ducky is in the database, and the other stuff in the scene is not. And as I said, the deer is in the database, and the other stuff in the scene is not. So in the bottom part, the points that pass through queuing are shown in yellow. So you should see that there's still room for improvement. There's all this junk over here. But basically every pixel in that image started out yellow. And we managed to carve out a fairly large percentage of them so we don't have to even consider them any further in our matching process, while still maintaining a fair number of those points on the deer, the ducky, and the plumbing part, respectively. Any questions about this? Okay. So, as I said earlier, I think I basically explained it already, but constrained correspondence search constitutes basically starting with a particular spatial neighborhood on your model, call it M1, and then comparing it to all neighborhoods on your scene, the naive way. And let's say you find a great correspondence between M1 and some S1, which is some signature corresponding to a point on your scene. Now, you can imagine, one way to sort of visualize this is that basically what you're going to do is think about, if you assume that this correspondence is correct, you're going to more or less staple that point of the object to that point in the scene. Or not staple is not the right word, but you kind of chain them together. So then you know that those points have to correspond to each other, and so that the range of possible transformations from the object to the scene has then been constrained. So if this is the object model and this is the scene, and I say that the thumb corresponds to the thumb, then I can really only do a limited amount of rotating and no translating at all, really, in order to make the rest of the object line up with the scene. Or not even to make the rest of the object align with the scene, just to respect that first correspondence. So then you only compare the next model signature to any scene signature if that correspondence is consistent with the first one. And so going forward with that analogy, basically if I have my two objects here and I've just decided that the thumb corresponds with the thumb, and my next point is the tip of my index finger, I am really only going to consider points on the right hand that are within the sphere of travel of the tip of my left index finger. So my pinky finger is not going to apply because I can't possibly rotate my left hand so that it lines up with the pinky finger. And so on and so on and so on. The first two correspondences, so if you find correspondences between the thumb and then the middle finger and the middle finger, that further constrains the set of rotations that can align the left hand to the right hand, and so on and so forth. So the problem, of course, is what if your first correspondence was wrong? And everything kind of falls apart after that because then you can't really recover from that initial error. Everything that you do follows from that error. So that's the key issue with constrained correspondence search. Transformation clipping I kind of already described also, and I think the picture at the top left here is really the take-home message. Let's say we have a mobile robot like our Mars Pathfinder, and this actually happens if you don't do transformation clipping, especially if you are building up massive indoor environments, such as the Chernobyl nuclear power plant that I told you about. You can have a robot that is going through a U-shaped hallway, takes a scan of this part, and then takes a scan of this part, and they're both kind of L-shaped, right? So it looks like a pretty good rigid body transformation that aligns the two, which just does rotation and translation. A pretty good alignment is to turn this one over on its head to align it with that one. The problem is that that's physically implausible, especially if you have gravity and your mobile robot is on wheels and does not turn on its head in between scans. So transformation clipping is basically a way to say, I know a priori that my range of possible transformations between views is bounded by some bounding box in that 6-dimensional space of possible rotations and translations. And this is just an example of this in a larger scene where we put limits on the amount that we think that our mobile robot moved in between scans. And so when we're trying to find a match for this point here in this data set, instead of trying to find matches throughout the entirety of the data set, we only have to look for the ones that are inside that box, which is a lot less than the total number of points. So this does two things. One, it makes the finding of correspondences between model and scene or between scan 1 and scan 2 faster because you're doing fewer of these comparisons. It also kind of stupid-proofs it by not allowing you to end up with this kind of matching. Okay?
Question.
Yeah.
The previous.
What was it? Constrained. The one before, yes, constrained correspondence search. Can you have such a mechanism so that you have a pretty good idea that this point and this point match, and then you have a pretty good idea that you found a consistent second match, but then what if you find a third match that is inconsistent? Can you sort of keep that off in a parallel queue and sort of build them up in parallel, and hopefully pretty soon one of your parallel matches, especially if you have a really noisy system, is going to outstrip the other ones by far, and you can say, I'm really sure, even though we may have found these other,
Yeah.
Yeah.
So people haven't really taken this idea. It's interesting, actually, in the 1980s, early days of computer vision image processing, like 1981, there was a popular notion of parallel hypotheses and multiple hypothesis tracking, where you would do exactly this. You would start to explore the scene pixel by pixel and point by point, maintaining a set of hypotheses about things like transformations from model to scene. And that every subsequent point that you looked at accumulated evidence for one hypothesis or another, or maybe multiple of them. So it turned out, though, that this ended up being computationally difficult. And so I think the field just decided to go away from that. So what could have happened is that we could have all decided, let's solve the data structure problem of maintaining multiple hypotheses in an efficient way, or let's just dump that approach entirely. And so what we ended up doing is dump that approach entirely. So for right or wrong. But now, interestingly enough, as that kind of went away from computer vision and mobile robots became more and more of a going concern, exactly that kind of multiple hypothesis tracking rose to prominence in mobile robotics. They didn't call it that. They called it probabilistic robotics, but I'm not. Don't be fooled. That's exactly what it is. It's maintaining multiple notions of what the world is like based on exploring it. So, all right, I should probably just go to the summary then, and you can read about constrained inconsistent correspondences. It's kind of not that complicated. So we use local shape signatures to deal with various problems related to detection, but the naive algorithm is slow and prone to stupid errors. So we try to either reduce the number of comparisons between the scene to the model, use our preconceived ideas about transformations, and basically try to reason about whether sets of correspondences are reasonable. Any last questions? Okay, see you Wednesday.